First of all, I'm extremely happy to kickstart these AI seminar series that we have put forward at the Technology Innovation Institute. And I'm quite happy that Pierre-Louis Lyons has accepted to kickstart the series. As you know, these series are done roughly every week with top scientists. And the objective is more or less to showcase the kind of new research which is being poured at the interface of mathematics, computer science, and AI, of course. So Pierre-Louis, I think nobody needs to introduce him. I mean, you can take a look on the web and see the astonishing work he's been doing. And I'm quite happy to know him because at the difference of many middle fields in the field that you may know, Pierre-Louis has been also very interested in applications and working in various domains of applications, going from basically the industry of flying like planes, Airbus, to things which are more of the climates, to things also where I had the opportunity to interact with him in the field of telecommunication. And his interest is quite broad and looking not necessarily only at the fundamental part of the things he's doing, but also at the application and trying to solve also some scientific problems that we're facing within our industry. Of course, besides that, he's professor at Collège de France, which is also a quite famous institution in France with top rank people, and he's having also a couple of positions here and there in various places in the world. So again, I'm quite happy, and especially also the title of his talk is quite intriguing for many of us, where he's trying to link basically a topic for which with one of his colleagues also, which is here, called Jean-Michel LASRY, they've been the pioneers, called mean field games, and trying to see basically the connection of this, I would say, astonishing theory to computation and neural nets. So, of course, now, Pierre-Louis, the floor is yours, and I'm quite happy to have you here and to host this basically seminar.
Thank you, Merwan. So first of all, my internet connection is not entirely stable. So my voice may break down from time to time for a few seconds. Don't worry, this is just my home line, which is not the bandwidth is not what it should be, and but it should be okay. Thank you, Merwan, for your nice introduction. I almost believed what you said. Indeed, it's a weird title: Computations, Neural Nets, and Mean Field Games. Okay, I know the last part, but I have some experience with computations, and I'm still very naive about neural nets. I'm honored to start this series, although the title is Artificial Intelligence, and honestly, I have absolutely no clue about artificial intelligence, but I'll come back to that point later on. I'm a mathematician, so interested in applications, so I'm also an applied mathematician, but don't worry for those who are not experts in mathematics. My talk is going to be light on at least, well, it's going to be light, period, but especially in terms of mathematics. Okay, so let's move on. Okay, now, I don't know how to, okay. So this is a short summary of a joint presentation with Jean-Michel LASRY. Jean-Michel LASRY, just move your hand if, Jean-Michel, if you don't mind. Move your hand so people see who you are. With whom we invented these so-called mean field games already more than 15 years ago, close to 20 now. It's a joint presentation with Jean-Michel LASRY in the sense that I will be speaking and he will be answering questions. No, I'm joking, but we will both be answering your questions. Well, there is this story of a famous mathematician that was touring in the States with his driver, and he got so bored by giving always the same talk that at some point he asked the driver to make the presentation instead of himself. And of course, there was one question, and he had absolutely no clue. So the driver answered, well, this question is so simple that I will let my driver, namely the mathematician, answer the question. So I'm the driver, Jean-Michel is the mathematician. Joint presentation with Jean-Michel LASRY of really a teamwork in Lagrange Center that Mayor 1 in Paris that Mayor 1 knows very well, since we are building it together, namely Yves Ajdou, Louis Bertucci, etc., etc. In all my presentation, whenever I say neural nets, or I even use the abbreviation N square or N2, I really mean artificial neural nets. All connection with neurosciences is purely coincidental. So an introduction, I expect that many of you have some experience with computations and know neural nets, but certainly very few of you know what min-field games are. So it's going to be very, very short, non-technical overview of min-field games, answering the questions what, how, why. I will make an interlude. So point 3 is really an interlude, which is a naive mathematician's view of deep neural net computation. So both the view and the mathematicians are naive, if you ask. So the fourth topic is really what we are currently developing with the team. And I couldn't resist the pleasure to call it DNA and the curse of big D. So DNA is really decision, neural nets, algorithms, and the curse of the dimensionality. So in point 3, I will try to present some approach to a mathematical formulation of what deep neural nets come, while in 4, I'm going to use neural nets to make computations which do not seem to be possible in with traditional approaches. So both sides of neural nets, the tentative explanation is a big word, or at least formulation, mathematical formulation, and by going backwards, how to use them for a special class of equations. We'll get there in due time. Next, introduction. This is just blah blah. AI or not AI? I don't know. I have no clue. Does it exist really, or this? I have no clue. Certainly, and honestly, I don't like so much the word AI because I'm an old guy. I was born in '56, so I'm 65. And so I already heard a lot computer scientists using in the late 60s and early 70s the word AI, promising AI for the next year or for the year after or for 2 years after. Of course, never came. It was not a complete failure because some good ideas emerged out of that, but clearly the promises were not kept. So I prefer to be very, very careful when talking about AI. But what is true, independently of whether we call it AI or not, is the fact that the recent the development of algorithms for the intelligent manipulation of data indeed look like some attributes of intelligence. So why not? Neural nets. Neural nets is both a very old story. I remember in the 70s, people starting to use, at least in France and probably earlier elsewhere, but someone like Robert Azencote was using hollow neural nets to make some automatic classifications of submarines. So at that time, only hollow neural nets existed, but already some of the successes that we have seen in the recent years were already present, or I mean, some toy examples were already done a long time ago. Now, of course, deep neural nets change the picture drastically. Although we will see that what we are using in the last part of the lecture are some kind of hybrid techniques which combine some math and neural nets, traditional neural nets computations. Those are not deep neural nets. They are not completely hollow neither, but clearly we should be able to work with 5-6 layers and maybe go, and I might have some time to explain, to 15 or something like that, if we want to get some more information than pure numerics. But I'm not sure I will have time to discuss that. Clearly, globally, whether they come from neural nets or more classical machine learning, classical in the sense of computer science / statistics, I'm thinking about k-mean, EM type algorithms. One need to understand better machine learning. That's important because we want to have some predictability, we want robustness, we want to avoid bias, and very often they are being used in the society, and there is of course the question of the social acceptability. And there is no way but to understand better what's going on in those algorithms. And for me, understanding better goes through math. Because I'm a mathematician, there is understanding is a word which have different meanings in different sciences. And so from my point of view, this means a mathematical improvement of the understanding of machine learning. There are many interesting works in that direction. Most use de facto mean field approaches, statistical mechanics, statistical physics. And I want to mention that at the next ICM, the ICM is the International Congress of Mathematicians that takes place every 4 years. So the next one is going to be in 2022. And there's going to be 2 plenary lectures which are connected, in fact, more than that, which are connected to machine learning, etc. One by Francis Bach, by the way, and one by Weinan E. Weinan E, Weinan, that's his first name, and his name is just the letter E. Weinan has been working a lot about mean field approaches to the justification of the use of deep neural nets. So there are many interesting works. They, in fact, all the mathematical attempts to understand use sooner or later some kind of mean field approach. There is also many connections with game theory and classical machine learning. I may go back to that. However, I want to point out that some applications that involve data. In fact, we had a startup with Jean-Michel maybe 10 or 12 years ago called MFG Labs, and in fact, our main success was in terms of data analysis for the movie industry, and we are, I think, pioneers in terms of commercial applications. Of big sets of data, and already some time ago. But we were dealing with humans, and with humans, they tend to have strategy. There is a famous example about electricity pricing, where when you announcing a new rate for electricity, change immediately the behavior of some big consumer. Who then got a very good price for electricity. Typically, this is the football team of the Sea Oaks in the States, because it was announced that the price would be computed by an average of the, let's say, last week or last month, I don't remember. So what they did was immediately turn all the big lighting they have in the stadium, consuming a lot of electricity for a week and then getting a fantastic price out of it. Yes, indeed, human beings are strategic agents. So clearly you need to combine data with something that takes into account how they will react to the announcement of a new rate, of a classification, whatever. There are many examples of that sort. So there are, this leads to connection with min-field games, and it goes both ways, both in trying to design some new algorithms, but it also goes as potential formulations, mathematical formulation of deep neural net. I want also to emphasize in this long introduction and so much blah blah, that neural net computations seems to be very well adapted for decision problems. So decision problems, some of you are too young probably to know what we used to call decision theory. Let me just say that it contains optimization, control, min-field games, etc., etc. In particular, so those type of computation for decisions problem are not exactly the same as those which are being made, let's say, in structural mechanics or fluid mechanics, where a certain degree of precision is needed. Much more important than precision is robustness of the result, and the way the result depends on various parameters, how it moves with parameters. And so N-square, I mean, neural nets computations are well adapted because precision might not be the best quality, but it allows to make huge, I mean, computations for big D, big dimensional problem, and in ways which can be used for this behavior in terms of various parameters. So it might offer, at least let's be reasonable and modest, a partial curse, a partial answer, sorry, not curse, a partial answer to the curse of dimensionality. Those words, curse of dimensionality, have been used by many people in the recent decades. Richard Bellman, I think, was the first one to coin this expression in the 50s, and precisely because of control problem and the use of the so-called Bellman equation, which is a partial differential equation in a space whose dimension is the number of coordinates of the state of an agent. So if you describe the agent that is trying to control a system, or see if you describe the system, sorry, with 7 parameters or 5 parameters, 5 variables, you are naturally led to an equation dimension 5, 7, and that's, of course, for traditional numerical methods, that's a problem. So we'll come back to the curse of big D later on. Okay, time to more blah blah about min-field games. So we introduced, as I already mentioned, with Jean-Michel LASRY, the subject more than 15 years ago, in several steps. First, some class of models, and then we invented the so-called master equation, which is an infinite dimensional equation. So forget even large dimension; it is infinite. Bad news for numerical computation. Since then, there has been an enormous development in math and application. There are probably more than 2 international meetings just in math every year. Applications to economics, finance, telecom, computer science, blah, 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 networks, cloud motions, arrays of robots, captors, even life sciences. In one sentence, it's a new class of mathematical models which combines ideas from game theory, Nash equilibria, and statistical mechanics or statistical physics, namely min-field theory, that I already alluded to when discussing, let's say, Wayne and E's work. So there is this min-field part, but it also combines for the behavior of agents with ideas that come from game theory. So behavior of agents, game theory, plus the idea of statistical mechanics, min-field theory. In some sense, a collaborator of ours a few years ago pointed out to us, this is just a tiny remark, that in some sense, we were doing a psychohistory. So you have no idea what the science of psychohistory is. You shouldn't have an idea because it doesn't exist. It was invented by Asimov in his famous foundation cycle. And for those of you who have not read the books and don't want to read books that were published in from 47 to 52, if I remember correctly, you can watch the new TV series Foundation, which is just currently be aired. And the point is that there is a character who is a mathematician invent a new theory which can predict the behavior of crowds, of huge number of people, and always insists that this cannot tell anything about the behavior of one person. And clearly there is behind that the idea of mean field theory, or if in simpler words, the law of large numbers, which is at the basis of statistic and probability theory. Of course, you have to build up quite a bit to out of that, but the law of large number simplifies what's going on, which is totally unpredictable at the level of one agent, but which may become understandable something that you can model using mean field ideas. So it allows to study situations or systems with a large number of interacting small players or agents or whatever you want to call them, plus possibly a few major agents. So let's ignore the few major agents for the time being. It's a large number of interacting small players. Small means that no single player, no single agent, again, a little bit Asimov-like, can affect the outcome of the, can really affect what the system is doing. So each agent on top of that is rational in a sense which is borrowed in economics, namely it chooses a behavior in order to optimize a certain criteria, taking into account the current state of the crowd and the strategy of the agents. In turn, this choice affects the dynamics of the crowd. So there is this idea of fixed point. What the state of the crowd affects what the agent is choosing to do. The agent, being rational, chooses a strategy which in turn affects the state of the crowd, because all the agents are doing similar choices. In other words, that's in fact a special case of mean field game. But those are words that some of you may be used to: multi-agent, dynamic equilibria, and they are models. But there is a but. Those are difficult maths and difficult to compute. Why? Well, there are new equations and new theories that to be built. There are now 2 research books, and for 5 to 6 years, I made my research course at Collège de France, 18 hours. Everything can be downloaded on the web. So there is more than 100 hours of mathematical research courses available, and this gives you certainly represent only some part of the theory which is not available. So there is no way I'm going to go into that. It's irrelevant for the purpose of my talk. There are mathematical theories that exist, and there are still many, many open problems, as always in math. Variables are, and these I want to go a little more slowly, are the state of a generic agent. So if you want to make an MFG model, you have a crowd. You have to define the state of a generic agent, like you do in system theory. When you take a system, you have to define the state, its dynamics, the way you can influence the system, you can control the system. That's typical system theory. So the state of generic agents, typically, not always, but in finite dimension. I don't know, your wealth, your height, the number of bits you have to transmit in the telecommunications networks, but also your level of energy in your device, etc., etc. So that's really how you want to describe a device, an agent, whatever. So that's a state, and that's traditionally finite dimensional. But you have a new variables, which is a state of the crowd, and typically it's a probability on the state space. It tells you, how many people are in that state in each particular state. Except that it can be a continuous probability, or it can be a discrete probability, depending whether the state space is finite or continuous. But in general, it's an infinite dimensional partial differential equations in the XM variable. So partial differential equation, I'm pretty sure that some of you know what this is. If you don't, it's just a mathematical equations involving derivatives of an unknown function. And it's in many dimensions, so it's not a differential equation, which is typically in one dimension, which is time. So partial differential equation, infinite dimensional, because among the variables there is m, which is always an infinite dimensional variable. Okay, bad news. There are two simpler cases where you can reduce the problems to finite dimensional problems. The case of, that's a little bit pedantic, idiosyncratic noises, which means that from one agent to the other, the type of noise experience is dependent from one to the other. In which case we have some backward-forward couple system of a Bellman-like equation that's for the part of the agent choosing, and the Fokker-Planck equation, which is really for the dynamics of the crowd. If we have a finite state space, it's also a reduction to a finite dimensional problem with nonlinear probabilistic system in non-conservative form. Don't worry about that. If you don't know those equations, they were new anyway. So in the end, no one knew those equations, and we had to slowly begin to understand what was going on. So the maths are understood globally okay. There are still many open questions left, but that's natural. Computing solutions in the simpler cases are okay, at least if the state space dimension is small. Okay, 2, 3, that's fine. If it's a continuous problem, if it's a finite state space, it's not so clear, but again, 2, 3. So that's very low. So how to compute solutions defined on an infinite dimensional space, or just a space with a large dimension, 5, 7, and so on. Okay, I don't have time to give you all those examples, but maybe I'm going to use words to describe how to use min-field games, and I'm stop about this, the story about min-field game. I'll go back to its numerical computation later on. It's what we call in French the Ola. Okay, and very often in the States it's called the wave. The Ola is what happens in a sports stadium, where typically you may have from 50,000 to 100,000 people, so a large crowd. And from time to time, people stand up, push their arms forward, upward, and then the neighbors do the same, and it creates a wave that propagates, and which is quite stable. In fact, there has been a lot of scientific study about the wave, because this is about the spontaneous formation. There is this idea of synchronicity and so on. So those are buzzwords, but they are also a very interesting scientific question. So I'm not sure that if our model of the wave is really relevant, but I think that you will see how it works, and this may be used, in fact, elsewhere than the wave. And in fact, it's being used right now for technological not breakthrough, but changes due to the evolution of climate. So, and you will explain why. So you clearly need to propagate some change in technology. So the wave, at least our model made a prediction, which is that basically, if the dimension of the, let's say it's a circle to simplify, of the inner circle, the first row of people in the audience, the first row in the audience, if we assume it's a circle but that roughly it always has the same dimensions, even if the stadium is much larger, many more rows and so on, but this inner distances or lengths are the same, and then the waves should always have the same speed. And in fact, it is true, and it has been measured very precisely, and the speed is universal. So how does one do min-field game for that? Okay, so you're gonna have two coordinates for an agent, namely an angle which defines the column in which he sits or stands, and then along that column is somewhere we are gonna take an agent and we're gonna use a coordinate for his position, in the sense, if it's let's say a coordinate z, if he's sitting, z equals 0, if he's standing, z equals 1, and if he's in between, that's z, which varies continuously from 0 to 1 as he moves from the sitting to standing. Okay, so this coordinate z, and the measure, what is the measure? Well, it's going to be the number of people in state z in a column. Okay, so it's really a measure in z, which is parameterized by the angle of the circle, which is in some sense the column itself. Okay, that's the states are defined. Now you have to define the dynamics and the criterion. Well, the dynamics is really z dot equal a control, because you can move, so you can change your position, but you're not going to change in the column. Okay, so next you have to define the criterion. Well, the criterion is clearly there is a cost for moving, kinetic energy, z dot square. There is a position cost, typically being sitting or standing is comfortable. In between, that's very uncomfortable. So there is a comfort potential, which is very concave. And third, mimicry. You want to be in the same state than the others, namely than your neighbors. Okay, so you translate this in mass. The black box, the min-field game toolbox produces an equation. You analyze this equation and you prove a theorem which says that if the mimicry coefficient is not too small, given a value of this coefficient, but not too small, there are only two, there is only one up to a direction reversal, stable periodic wave. And so that's why it should always have the same speed. Okay, once more, this is just an S example. When I'm using the word S example, this means simple, silly, stupid, whatever you want. But I just wanted to give you the flavor on how to use min-field games. The mathematical details are irrelevant. Okay, now I'm coming to the interlude. A weird transparency. Well, there are two slides, in fact. The source, if you want, if you really insist on having more details, is a seminar I made at Collège de France. It's online, downloadable, and so on. There is beginning, after a few years, there's beginning to have some further works, not directly inspired by the seminar, but in the same direction. So inspired by the seminar, but not directly following up on the seminar. There are also connections with min-field games. In particular, I'm referring to a recent work by Mathieu Laurière and his collaborators. And Mathieu, who is a member of our team, or was a member of our team, is currently at Google Brain, in the Brain team in Paris. So what is the idea behind this very naive mathematical formulations of deep neural nets? First of all, in each layer, I'm assuming that you have a large number of nodes of neurons. So you can replace that, and the layer might not be in one dimension, but even in multi-dimension. So you're replacing this by X, which is in RD. So you have a large number of layers, okay? And this is, of course, a very, the first one, essentially all the mathematical presentations of formulations of deep neural nets, many use that type of idealization. The next one is, of course, a more even more brutal, because it's saying that you have such a large number of layers that you're going to replace it by a time, a t, which lies in R. And so, you know, forward processing along layers is really moving positively in time. Backward processing is moving backward in time. Next step in the mathematical formulation is that forward processing along layers is a Fokker-Planck equations. I don't have time to get into that. And the net parameters are the coefficients of the equation. And minimizing a certain loss function becomes a control of a Fokker-Planck equations via its coefficients. Okay. So here is a very simple example, more connected to image processing than to anything else. So you have learning data, U1, UN, with reference data, phi1, phi-n. Let's assume that you want to classify images. So here's the Fokker-Planck equation. There's going to be very few equations. It's going to be probably one, the first one, and they're going to be probably about 3. So this is what I meant by Fokker-Planck equation. So you have an equation by k varies between 1 and n. Let me go back. So U1, UN. So that's the size of the sample. Huh? So you have n coupled equations, and you have coefficients which are alpha, beta, gamma, where this is a linear propagation of information from one layer to the other, and a function of delta and uk, and that's all the operations you may want to do, like a nonlinear operation, like a plus part, truncation, sigmoids, convolution, and so on, and there are parameters there. And of course, you can specify, if you want to have convolution kernels, you can specify the f. All those coefficients are really the parameters, and which becomes functions of xt. And minimizing the loss functions, here I'm not making explicit the type of norm, is really trying to minimize what you get, let's say, at time 1 out of the equation, and the reference data up to a permutation. So that's phi, not phi of I, it's really phi at the index, which is theta of I, and theta is the permutation. Transport-like, Wasserstein-like type permutation distances. And okay, so that's one way to think about what we do with a deep neural net. Again, there is no need to criticize the model. I'm perfectly aware that it's very naive, simplistic, and so on. But let me just mention that the optimality conditions, when you have a control problem, you have something which is called the optimality conditions, which are necessary conditions to be a minimum, which involves, of course, the direct equation, equation number 1 that I wrote down, and a backward equation, which is, of course, a lurking backward equation, which allows to determine the gradient of the loss function. And this is completely consistent with the backward propagation of the gradient in neural nets computation. It's really the same, except here is a formulation, a compact formulation that allows maybe to get a better understanding for what's going on. Does it provide a framework for future analysis? Is it useless? Maybe, probably, is an answer I can make to both questions. So that's the end of the interlude, and I want now to. I'm doing okay on time. I have 15 minutes left to. Well, I have. I don't want to use a full hour. I have 3 more slides, and I want to leave some time for questions and so on. In fact, I never ask you, Merwan, how long I'm supposed to speak. But 50 minutes, it's 55 minutes is okay?
50 minutes is totally fine.
Okay. Because I didn't pay attention to what should be the length of the lecture.
Yeah, it's 1 hour, 50 minutes, and then we leave the rest of the time for some questions.
Okay. So I won't be too long. I always worry about the too long thing. Okay, you see in the title, dn square, the 2, it would be nicer to put it in below the n, and we should add an h, a little h in front, h and d, or d2 in fact, because that's decisions, but it's also dynamical and neural nets a. And the curse of big D stands for the dimension, of course. Okay, so why neural nets or any other means for computation is there a chance to be able to compute large dimensional control equations, so-called Bellman equations or Hamilton-Jacobi-Bellman equations, and min-field games that, as I already mentioned, can be even infinite dimensional equations. The answer is that in many cases, because we have some mathematical understanding of those equations, we, in many cases, but not always, we expect some kind of low complexity of solutions, okay? That somehow there should be not really hidden variables, but we are trying to find a function on a big space. But we expect in many cases that that should be some kind of explanatory variables that we don't know beforehand. We have no clue what they are, but there shouldn't be a large number of such explanatory variables. So it's more like a hunch, but it's also what we see in whenever we can make computations. So this certainly requires some assumptions on the type of Bellman equations and min-field games. What they are right now, we don't know, but we have the intuition that in many cases, because of the application, either in telecommunication or in economics, that solutions should have a relatively low complexity, depending on a relatively low number of unknown variables. Otherwise, if you add a high complexity, that's another ballgame. Maybe one can still do something, and I think I can already mention that that our next step might be to tackle problems which have some intermediate complexity, in the sense that they have singularities whose location is not known beforehand. That's complex because resolving a singularity is complex. That's a much bigger complexity than smooth solutions. But apart from those singularities, the rest of the solution should have a low complexity. So that's why I'm mentioning these as future work for intermediate complexity. Anyway, so this led us to design some hybrid methods which combine the efficiency of neural nets and all the mathematical qualitative understanding of the solutions that we build over more than a decade of efforts. Okay, I want to mention a simple static min-field game. I don't really have don't want to. This is more in the MADAM category, namely or hyperbolic systems. Forget the expectation that's because there is a Brownian motion. So you have two lines. Second line involves the Brownian motion. You can forget about it to simplify even more. You have the value function of the mean field game that you're looking for that solve an equation, but should solve some kind of a fixed point system, fixed point equation, which is not at all obvious. In fact, it's a consequence of the master equation. We call it the localization principle, in the sense of here we can localize in time. In fact, if you want to make if you're more familiar with dynamic programming, Bellman wrote an equation, but before writing the equation, he wrote down, he explained to us the optimality principle, which can be explained with a sentence, which is, if you take a piece of an optimal trajectory, it's optimal for the problem corresponding to that piece. And for such mean field games, of course, there is no optimality. That's game theory. It's like a piece of an equilibrium, a piece of an optimal between quotes trajectory is still optimal. But of course, you have a new problem that still starts at zero, but finishes at with a finite horizon, while in the beginning it was an infinite horizon problem. And so the U appears on both sides because you have reduced the time interval. So that's what we call the localization principle. And there is a further nonlinearity. That's the feedback loop I was mentioning, with the crowd affects the individual through its choices affects the behavior of the crowd. And you see it here in the sense that the dynamics, which is the second line, depends on you, and the cost, which is the criterion, the F, depends on you. So it's a highly nonlinear problem where everything is coupled. But that's what we are going to solve through neural nets. And the X lies in our K. This is really where K is large, possibly infinite dimensional. So T is fixed. In fact, we are going to choose it small and make an expansion. Tau is just some discount factor. It's given. F is given. And X, as I said, lies in our K, and K is really the dimension of the state. Okay, so possibly large, even infinite. So that's a problem that we want to solve. So there are various mathematical pieces, which is, first of all, to reduce the fixed point part by having some simple iteration. So observe that it's still a fixed point, but in all the nonlinearities, we are using an iteration, okay? There are convergence theorems, so there are mathematical good facts lurking behind. I don't have time. In the regimes which corresponds to low complexity, namely smoothness. So this converge. Now, first implementation. So the first implementation is to think that we are going to approximate that the equation that we want to solve is really un plus 1 of x is epsilon, because t is now epsilon, f of x epsilon plus e minus 2 tau epsilon un plus 1 of x epsilon, while x epsilon is given by the iteration. So we are at a stage where somehow we have built un, and we want to find un plus 1 that still solves a fixed point equation, and the dynamics are known if we know the point x. So typically epsilon is like, in our example, like tau divided by 100. Okay, so that's the first step in the implementation. What is the problem that we want to solve through neural nets? So the the second implementation is really suppose that we have a sample of the points in the state space, x1 to xn. I will, the third step of the implementation strategy will be how to build those points. Suppose that we know those points, then the parametrization and the choice of the parameters through an optimization problem, which involves a certain loss function, is done through a neural net. So you can call it learning, or saying that the parametrization and the optimization are being done by the neural net. So you are now trying to minimize this expression, where you recognize the UN guy which has been given and which needs to be defined everywhere, but you're using the parametrization, the implicit parametrization of functions in the neural nets. We are, the numerical simulations I will present are done in the Google world. So in particular, I mean, we are using their facilities which are being offered, but not free, to the research community, and we are using TensorFlow. So by this, I want to illustrate the fact that from a purely neural net point of view, we are doing things which are quite simple. The architecture is quite simplistic, not so many layers, something like 5 layers. Very traditional architecture, very classical architecture, although we are envisioning for an infinite dimensional problem something that might be slightly more sophisticated, and if I have time I'll come back to that. So standard neural nets which allow to, if we have chosen x1, xn, to build up UN+1 at those points, and thus UN+1 through the neural nets in some sense everywhere. So what about x1, xn? How do we choose the points? That's where also we bring in all the mathematical understanding we have of the problems. So I tend, we worked with Jean-Michel quite a lot on Monte Carlo simulations. So in Monte Carlo simulations, you know that there is something known as important sampling to reduce the variance. So in some vague sense, it's some kind of heuristic important sampling. Or in other words, everything that we know about what the solutions look like, we throw it in there in the selection of the family. And we can use also some Monte Carlo sampling, but with the information that I was mentioning. We built, for instance, for min-field games in infinite dimensions, X may be even in 1 dimension, but then M is a probability measure in 1 dimension, right? So that's an infinite dimensional object in 1 dimension or on an interval. Let's simplify 0, 1. And we are currently running numerical experiments on a famous problem that was designed by Cressel Smith. It's a famous paper in 1909, if I remember correctly, a famous paper in economics where, in fact, which was pointed to us by a Nobel Prize in economics, Bob Lucas, and he told us, you know, this paper is a min-field game. Of course, no one knew what a min-field game was at that time. So they just defined a game for a population in economics, for a population. And they devised a numerical strategy, which was a huge Monte Carlo simulation and a representation of the space of measure by their moments, their first 10 moments. This was really amazing done at that time. but not very easy to build. It's not very easy to build a privacy measure out of its moments. And so we are now currently using a discretization which relies upon all the mathematical understanding we have of what the solution should look like. Namely, that instead of using x, one should use x squared. Namely, that what is very important is the point mass at the lower end point of the interval, and so on. And this leads to a more physical discretization of the space of priority measures. And we are currently running the experiment. A few more slides about an example for which we finished the numerical computations, which is a series of work we have been doing with Jean-Michel LASRY, as usual, with the Bertocci brothers, Louis and Charles, which is about cryptocurrencies and Bitcoin mining, and there are various aspects. So I'm not going to go through all the slides because you must be getting tired. But it's about understanding the competition between miners and understanding the dynamics of investment and spending of miners, and also understanding the dynamics of the computational powers of machines that are being used by miners, new generations of computers and so on. Yeah, so just for the sake of it, the market cap of Bitcoin, $1 trillion. Of course, what's crucial is the Bitcoin blockchain and the famous proof of work as a protocol for the blockchain. Proof of work is terrible from an energy consumptions, but our models adapt. If you want to try to see what is the energy consumption of other protocols, that's also something that we can tackle. Blockchain mining revenue, okay, that's it. The revenue fluctuates like Bitcoin values. The miners share revenue according to computational works. New machines produce more computations than old machines. Value functions of new and older machines satisfy a high-dimensional nonlinear mean-field game PDE system, enfolding the investment flows, miners, mining hash rate, and so on. So that you see a complete mean-field game equation. That's a bunch of equations. There is a decay just after the big sigma, which stands for a partial derivative. And that's again a hyperbolic system. And there is even except that there is even some probabilistic term, which is the last term, which is D2RR, which is a second derivative. Okay, whatever. So this is the type of equation. And thanks to the new hybrid solver, we can now solve this this master equation. There are a few examples of our computations. I don't really have time to get into that. Let me just say that here we are dealing with a situation where 7 coordinates, so it's in R7, and we don't quite know how to represent the functions that we are finding numerically because they depend on 7 dimensions. And so what you see as a one-dimensional objects are just slices. Next thing, and I don't have time to explain that we are very careful about the validation of the computations we make. So and there are also some mathematical ideas there, which is to say, does the thing that we get really solve the equation? And this is something that we can check using standard numerical approximation and Monte Carlo simulations, and we can check that at points. Not everywhere, but at points. Of course, if you sample the points, you get a pretty good idea that you have indeed completely solved the problem. So we solve it at a bunch of points. Here there is another validation, which is to compare with a one-dimensional computation. You see on this example how simple the function looks. That's the only comment I want to make. And so that's an illustration of problems with low complexity. And I believe that's one of the reasons why we are able to solve them with this type of combining some mathematical understanding and neural nets. Maybe one can do much better than that with even high complexity, but certainly we want to be careful. That's where we stand. That's what we can do. And we will see in the future, and I'm sure that there will be other works, and there are also other works with using different approaches, but I don't have time to get into that. I think it's a good time to stop, to let you breathe, and of course ask questions if you have. Don't hesitate to ask questions even if you are not too sure about the math. I'm not too sure about many of the subjects I touched upon today. So let's talk. Thank you very much for your patience.
Thank you, Pierre-Louis, for the presentation and the effort you made to make it very deductible for all the audience and clear. And I'm also very happy to see that there's now a new trend on, I would say, the computational aspects of MFG, which makes it now more relevant for the industry to start implementing your techniques rather than having these continuous formulation. And you've been spending a lot of time in terms of understanding how to implement those techniques. So that's really great. So there are two questions, in fact, in the audience. I mean, of course, I can ask questions for hours, but I'm here to the moderator, not the person who asked. So one question, the answer, I think you have it, is can mean field games be used for other collective systems different from deep nets? And the guy says, it's Eliseo Ferrante, I'm thinking about collective motion dynamics.
You don't have to read it. I'm reading. Yeah.
Okay, sorry.
This is okay. I'm finishing the.
No, take your time.
Okay. That's an excellent question. Yes, the answer is yes, and it's being done. Okay, so first of all, about collective behavior. It turns out that there is a group of physicists that have been developing mean field games after our work. So I'm very glad. Usually mathematicians tend to work on problems suggested by physicists essentially 30 years after the physicists wrote down the equations. This is one example where physicists are working on equations written down by mathematicians. And they bring something, obviously. In fact, there are two groups of physicists, one of which has been working on the collective behavior of fishes. So it's not bird flocks, but it's fishes. I've always thought that it was relevant for bird flocks. I've never done it. And I'm perfectly aware there are simpler models which are being used, which used Newtonian dynamics or even mesoscopic models for bird flocks. Although those are ad hoc models with parameters and which are then fitted against observations. So, for instance, for birds, this has always been in the back of my mind, especially when they are doing long flights. They use single lines flights. And clearly, this is related to energy because of the wind of the air resistance, and wanting to be together, and so on. So it should be there. The triangle formation also is very aerodynamic, and so in terms of energy, it's more compact, so they are closer to each other on average. But I've not pushed further than that. The answer is yes. The answer is that there is no opposition with simpler models like agent-based models, because in fact, agent-based models are limits of min-field games, where you let the intertemporal preference rate. So typically in a criterion, the cost that you assign to a certain period of time will not be in general the same if that interval of time is 1 year in the future or tomorrow. Okay, so usually, not always, usually what happens in a year from now is less important than what happens tomorrow. Okay, and that's precisely the so-called intertemporal preference rate. And when it becomes very large, you somehow narrow your horizon more and more. When it becomes infinite, you're back to an instantaneous decision, which doesn't take into account any kind of perception of the future. And those are agent-based models, okay? So it's like there's a continuum of min-field games, and at the boundary, you have agent-based models. So I'm perfectly comfortable with that. You're also raising, I'm extracting a few keywords from your questions. You're also raising the ideas of phase transitions. So all physicists are aware that min-field theory is like step 0 in the study of complex systems. Law of large numbers, step 0, and then they are interested in fluctuations and phase transitions and so on. We have been stuck for a long time to try to understand what phase transitions meant in the context of min-field games, and it's no surprise that a group of physicists in Cergy-Pontoise gave us the answer. Explaining to us that in some sense, when we were varying the parameter of our models, those are like order parameters, and you can have phase transitions from one type of equilibrium to the other. So it was right in front of our faces, and we couldn't see it. And they did that, this phase transition analysis, on another simple problem that was in my slides, but I didn't want to describe because I didn't want to take too much of your time, which is when does a meeting start? Okay, so typically people want to attend a certain meeting, large number of people that want to attend a certain number of collective meeting. They have random times for their transportation, especially if they are living in Paris, and basically, being on time is certainly a plus for the others. I mean, we are polite beings, but being there half an hour before is irrelevant, okay? So there is no gain in being there too early. Being there a little bit late, but at least before the meeting starts. We are in a country like France, where meetings always start late. So that's okay, because at least the meeting has not yet started. And then the meeting will start when not everybody has come, but let's say 80 or 90% of the people have come. And then, of course, if you get there after the meeting has started, it looks very bad. So you have a cost profile, which is like a 3-step function. You have this element of randomness and so on. And the question that you raise is not what you will do, but at what time the meeting will start. if everybody has the same type of strategy, share the same type. And so clearly you have parameters, which is what is the ratio between the various slopes. You have 3 slopes, you have 2 ratios, 2 parameters. And there are different types of equilibria depending on those parameters, and you can complexify the game a little bit. And typically, it was observed that you can have a phase diagram in view of those phase transitions. This is a slightly paradoxical situation in the sense that phase transitions may not be something which in statistical physics cannot be, and I agree with your comments, cannot be modeled, cannot be studied through mean field theories, okay? Here, phase transitions might be something else. Okay, so that's one answer to your comments. There are further issues about large deviations, fluctuations, and so on. And we have currently no understanding whatsoever of those issues. There is another question by Assad. Yes. If you allow me to use your first name. The first question I commented a lot was by Eliseo. Which level of mathematics should be learned? Well, everybody can by graduates to implement real-time hardware-based applied artificial intelligence for deep learning. Well, I don't know. Right now, the data scientists or engineers or technicians that I know are being trained at a serious mathematical level, at least in terms of probability and statistics. I'm not sure it's really needed. In fact, some engineering schools I'm aware of use very little mathematics, which would be what? Which would be master level, classical master level in mathematics, and learn how to use some commercial solutions. So it's quite difficult to say that. I have to say that there exist now commercial solutions where you basically need to know very little in order to be able to try those commercial solutions on applied problems. But there is a law of conservation of difficulty. So if you have to tackle a really difficult problem, this won't suffice. So knowing more about neural nets, knowing more about probability, and possibly knowing more about math, but essentially probability and statistics, that's certainly a plus. Now, it's a different ball game. I could also answer the question, which level of math do you need in order to use mean field games, which is a slightly different story. If you want to do research on mean field games, you need quite a lot of math. But someone like Louis Bertucci is not a mathematician. He was trained as an economist and as a PhD thesis in finance. So he has a master plus understanding of math, and he was able to catch the essential of mean field games in order to use it. In fact, one of our economical collaborators, Benjamin Moll, who was in Princeton, now is, I guess, in Columbia, a student of Bob Lucas, was teaching mean field games in master classes in economics. So you can learn quite a lot of mean field games with a moderate mathematical understanding. Of course, not all. And one can find material on that online. Okay, now if you want to solve if you want to solve mean field game with neural nets, you'd better know quite a bit about both subjects, and that's why we need to learn more. We are still in the stage of learning more. Okay, I tried to understand, to answer your questions, but I'm sure that one may also participate to that discussion, because he has hired many people that had to learn such hardware or software solutions.
I had the experience exactly in implementing aspects of AI, and of course the combination in terms of mixture related to I wouldn't say a differential equation that is needed, but more basically on solvers is extremely important. So optimization for sure is the big thing at the moment in terms of skills that is required.
Yes.
I think we took a lot of time from you, Pierre-Louis. I would like to thank you. I have a small comment to tell you, is that we all know that middle fields is before the age of 40, but Nobel Prize is unlimited. And as you know, a couple of days ago, they gave the Nobel Prize for complex systems. As you know, Parisi got it. And that reminded me when I saw the transition. And I think if you would work a couple of years more, don't retire right now, on complex systems using infield games, you may have a chance.
That's kind. But you know, you remembered the fact that there is no Nobel Prize in mathematics. Instead, there is this variant, which is quite different, in fact, because there is this age restriction of Fields medalists, and there are various stories about why there are no Nobel Prizes. One which is false, unfortunately, because which is the traditional one, that the most famous mathematician was of the times was a professor in the same place as Nobel, and they hated each other. So the usual story is to say that not only they hate each other, but that this guy was in fact Nobel's wife lover. That's completely wrong. Mathematicians do not have time for that. They are doing math all the time. No, I'm just joking. And and the true explanation is that indeed Nobel hated so much the mathematician Guts that he certainly didn't want to give a prize to this guy, and most probably this guy would have gotten it if he had made a Nobel Prize in mathematics. Now, Parisi is a very good friend of mine. He's a good friend of mine. I mean, I remember that was a few years ago before COVID and everything else. Parisi gave me in a bar his recipe to make limoncello. And his limoncello is indeed pretty good. So he can do, but he's a fantastic physicist. You know, I cannot pretend to do things at that level. And one should never work in order with a goal which is to get a prize. We work because we love what we do, and prizes are just irrelevant.
Side effects.
That's a message for younger people too. Huh?
Very good. I don't know, maybe one last question, because I know you're tired. There's Maximilien Germain who's asking you about the question about the master equation. Can you read it, and then we'll finish with that?
So Maximilien is there, right?
Yes. Maximilien Germain, last question about the ubiquitous master equation, which is always there.
So Maximilien, what I explain with is if you want to call it the Wasserstein space, the space of priority measure, is what Krasser and Smith did using moments. We are not using moments. We are replacing a priority measure 0, 1 by a combination of a point mass at 0 and masses on interval of lengths, which are related to our understanding of the such Krasser-Smith problem. So that's how we approximate the space of measure. It has nothing to do with either randomization or moments. That's a specific answer. Okay.